Hi, my name is Yu Xiaoqi. I'm a computer engineering student. Welcome to my final report of system engineering. Today I'm going to talk about nuclear plants. First is an overview of my presentation. I'm going to talk about what's the background of nuclear power plant and the future development of nuclear power plant, and develop my system and talking about the challenge we are facing. First is a background of the nuclear power plants. Electricity energy is an indispensable source of energy for human beings. Power station generation converts all sorts of energy into electricity. There are three main power stations all over the world. First is the hydroelectricity power station. The hydroelectricity generation station is a plant that produces electricity by using water to propel the turbines, which in turn drive the generators. This power station generates about a quarter of all the electricity used in the world. Second is a wind power station. Wind power or wind energy is the use of air flow through wind turbines to provide the mechanical power to turn electric generator and traditionally to do other works like wind power is a sustainable of renewable alternative to burning fossil fuels and has a much smaller impact on the environment. Third is a thermal power station. A thermal power station is a power station in which heat energy is converted to electricity power. In most of the places in the world, the turbine is steam driven. Water is heated, turned into steam and spins a steam turbine, which drives the electrical generator. This is not much different in nuclear power plants. Instead of burning fuels, in nuclear power plants use the energy from nuclear fission in nuclear reactor. Next, I'm going to talk about what the world's future energy needs. Abundant electricity supplies is an essential basis for countries eager for economic development. But more than a third of the world's population, more than 2 billion people, still live without electricity. And about 2 billion people consume less than 1 watt of electricity per person. By contrast, the per capita electricity consumption in Japan, France, and other economically developed countries is over 8 million, and the per capita real electricity consumption in the United States is over 15 million. If governments in developing countries want to build their economic and improve people's living standard through economic development, they must increase the use of electricity. According to projection of future electricity supply demand, it will double in the next 20 to 50 years and triple by 2050. The state of world nuclear power generation if delayed. What is the mintage plan? According to the World Nuclear Energy Association in August 2012, there are 435 working reactors in 31 countries. The vast majority of planned nuclear plants are also concentrated in Asia, where nuclear power is growing actively, while new plants in Europe and the United States remain stalled. Since the since the 1950s, nuclear power generation has experienced a history of more than 60 years, providing about 17% of world electricity. People have fully recognized that nuclear energy is an economically safe and clean energy source, and it should and must play massive roles in the world energy demand in the future. Although there is still no noticeable recovery in new nuclear power plants of advanced nuclear power developing countries, many superior nuclear power developing countries led by US put forward proposal for future generation 4 reactor at the beginning of the decade in the face strong electricity demand in developing countries. The purpose of this. Next, I'm going to talk about why we need nuclear power plants. Nuclear power plants is a power plant that a large amount of energy can be taken out with a small amount of fuel. A large amount of power can be stably supplied. There is no localized distribution of fuel resources, aka that means the nuclear fuel stabilized procurement. It has high fuel storage ability and contributes to improving the national energy self-sufficient rate as semi-domestic energy. And the nuclear power plant does not emit greenhouse gases that cause global warming during power generation. The prospect of fourth generation of nuclear power plants is that most of fourth generation nuclear energy technology consider the comprehensive utilization of energy and use the advanced thermal cycle to produce electricity as well as hydro, seawater, dissolution and other process. The the difference and advantage of the fourth generation nuclear power plants is that nuclear waste for the fourth generation of nuclear power plants remain radioactive for a few centuries instead of millennia. 100 to 300 times more energy yield from the same amount of nuclear fuel, broader range of fuels, and even unencapsulated new fuels can be used for the fourth generation of nuclear power plants. In some reactors, the ability to consume existing nuclear waste in the production of electricity, that is a closed nuclear fuel cycle, this strengthens the argument to damn nuclear power as renewable energy. Improve operating safety and the fourth generation of nuclear power plants improve the operating system safety feature, which is the most important part, such as depending on the design, avoidance of suicide operation, automatically passive reaction shutdown, avoidance of water cooling, and the associated risk of loss of water, like leaks or boiling, and hydrogen generation explosion and the contamination of coolant water. But we're also facing some challenges. The first is the risk of an accident. A nuclear power plants, various layers of safety measures have been implemented, but the risk cannot be zero. It is, it is not permitted to cause such a nuclear disaster again. Reactor accidents are the single most significant financial risks facing the nuclear industry. Initialized estimates put the cost of damage at the Fukushima plant at $200 billion. Second is the issue of high-level radioactive waste. In terms of technology, geological disposal, embedding in deep underground formations that have the ability to confine matter is internationally accepted, but the disposal site have not been decided yet. Thirdly, it is necessary to point out the nuclear weapon can be diverted as a weapon and that can be exploited for tourism as a potential risk. Next, the advanced reactor technology can be characterized by the coolant they used and by the neutron spectrum as shown in the following table. The coolant transferred that heat produced in the reactor to the electrical generator or other system that utilize the heat. Next, I'll start providing a brief description of different types of advanced reactor, which can range in power output from micro-size, that is less than 10 megawatts of electricity generating capacity, to small module design. First is a small modular light water reactor. This is a term that has been coined with small LWRs with a high degree of passive safety. SMR design encompass plants with electrical generating capacity of less than 3 megawatts. For an individual module, the SMR design being offered by NuScale Power is the most mature concept in this technology space. It consists of multiple 50 megawatts reactors that use a common water pool as their unlimited heat sink. The NuScale's design and similar concept leverage a large operating experience of the current LWR fleet with smaller and simpler configuration. Next, the module high temperature gas cooled reactor. This term describes a graphene moderated helium cooled thermal reactor. The reactor is low power density, coupled with a high heat capacity graphite modulate and robust trestle coated particle field provided a high degree of inherent safety. Two designs are where to exist. First, a premistic graphite modulator block that contain a graphite cedar laden with a trestle particle, and the third, a pebble bed made of a cue ball size graphite pebble, also containing trestle fuel particles. The gas-cooled fast reactor is described a graphite is a high power density fast reactor cooled by high pressure helium. The sodium fast reactor is a type of fast reactor is cooled by liquid sodium. It operates at a very high power density given the absence of moderator and the excellent heat removal capacity of the sodium coolant. Most of the design under consideration today are small SFRs that have inherent and passive safety features that may not be viable in large sodium systems. These concepts have the potential to reduce cost but require additional technology development. The MSR class reactor uses a molten salt as both coolant and fuel because the fuel is dissolved in the salt. There are both thermal and fast variants of this design. The thermal system uses a fluorable salt with graphite or another material as a moderate to slow the fission neutrons down to thermal energy. This fast reactor variant uses colorant salt. A variety of conceptual designs have been proposed, all of which require significant technology development. Nuclear reactor system can be compared using key parameters such as operating temperature and the neutral damage to important core structure, such as the fuel cladding, that limit operational condition. A key metric for the level of neutron damage is a neutron-induced displacement at atom from their original position in the material lattice, which is measured in terms of displacement per atom, dPa. The level of damage is a function of the material being tested, the damage probability, the neutron spectrum, the neutron flux, and the irradiated time, high level of displacement damage, high dPa, challenging a material ability to perform its function in the neutron environment. This level of displacement damage can be determined the lifetime of the component, which may have to be replaced once that level of damage exceeded. New radioaction-resistant material may be required to accommodate damage level in excess of 200 dPa. The right figure shows a neutron damage temperature operating window for LWR, which is generation 2 to 3 and SMRS, and for different generation 4 concept. The damage level shows in the figure that the value expected for both fuel cladding and structural material in the reactor core. For shield-loaded bearing component, the damage level will be much lower. LWS, including SMRS, operate at a low outlet temperature, approximately 300 degrees, and low damage level. It's about 5 to 60 dPa. Note that with the life extension, 80 dBA is being reached in some existing LWR. For the VHTR and HTGRS and FHRS, also operate at low damage level, that is less than 5 to 30 dPa, but high temperature, above 60 100 degree to 950 degree, component in fast neutron system such as the SFR, LFR, and GFR are fast spectrum as MSR are subjected to much higher damage level, that is 50 to 200 dPa, and operate over a range of temperature 400 to 1000 degree. Depending on the design concept, the figure includes the TWR and SFR concept that proposes to reach damage level up to 600 dPa because of its long-lived core. Also, of course, we are facing some technology level to building the Generation 4 reactor, but the safety of nuclear system can be thought of a series of is the most important part of building the new generation of nuclear power plants. The safety of nuclear system can be thought of as a series of safety functions that must be satisfied, accomplished to control the reactor when it is operating normally and to remove decay heat when the reactor is shut down, thereby preventing the release of radioactive material to the environment in the event of an accident. The safety character, including but not limited to the following. First, the controlling nuclear reactor ensures the heat is transported to the final heat trap. Control coolant stock to prevent the loss of flow. Minimize the release of chemical energy. The reliability of startup device and decidable safety system operating device. Next, we talk about another topic of the challenge we're facing and we try to deal with. What about move the nuclear power plant to the underground? The construction of large underground nuclear power plant open up for a new way for the safety development of nuclear power plant. A prominent Soviet nuclear physicist and the father of the hydrogen bomb wrote on his memorial, frankly speaking, since mankind cannot abandon nuclear power, we must seek new technology means to ensure the absolute safety of nuclear power plant. One of the solutions that I favor is to build a reactor deep enough underground so that even in the event of worst possible accident, radioactive material does not enter the atmosphere. It is technology for about the building nuclear power plant underground. First, it is technology feasible. In terms of nuclear technology, it is perfectly feasible to put the island underground. At the same time, existing underground engineering, design, and construction technology can fully meet the need of underground nuclear power plants of a millionaire kilowatt class nuclear motor group. Second is a highly security. A wall rock is added as a physical barrier for underground nuclear power plants, which can effectively resist extreme external man-made events such as tourist attacks, improve the ability to resist extreme natural disaster, and significantly improve the seismic performance. Nuclear security measures are simply and effective by making use of the inclusively of underground cavern. It is easy to practically eliminate the possibility of releasing large amounts of radioactive substance from the design, and more conducive to the prevention of control of radioactive substance diffusion under the serious accident. Third, it is economical reasonably. Considering only internal cost and a crazy of less than 12 is the cost of underground nuclear power plants. Next, we talk about the importance of developing underground nuclear power. The underground nuclear power, it is easy to virtually eliminate the possibility of releasing large amounts of radioactive substance by design, and it is effective to the end of royal and people for the matter. It increases the ability to withstand natural disaster at royal end. Simply effective nuclear safeguard. It is beneficial to increase the utilization rate of nuclear fuel as well. Due to the change of the operating environment of underground nuclear power station, the overall layout design of underground nuclear power plant stations at home and aboard, and factors such as Chamberlain stability and the topological and geological conditions of the plant site should be considered comprehensively. The general layout of the underground nuclear plant is as follows. First, it should be reasonably arranged each building to meet the functional requirement of each system and meet the safe operation requirement of nuclear power plant. And it has to considering the characteristic of the underground engineering. It is advisable to reduce the scale of underground buildings. Nuclear island-related buildings should be placed underground and arranged as compact as possible. Third, the space characteristic of underground building should be fully utilized to realize passive cooling system, three-dimensional traffic pathway, zoom multiple layer security. To build the underground nuclear power plants, first we need to classification of the building. The nuclear power plants building are classified into substance and subsurface, and the function and the safety level are analyzed to identify which building need to be placed underground. The cost of underground nuclear power station is generally higher than that of subsurface nuclear power station. Therefore, the nuclear power plant building are classified into subsurface and the function safety level. And the layout of the underground workshop, the reactor plant is a core. Other plants can be arranged around it. The overall layout of the underground nuclear power plant should be reasonably planned according to the location of the underground plant and the building on the ground, and coordinate the functional requirement of operation, maintenance, and transportation. The general layout is directly related to the topological and geological conditions of the site. We have four assumptions. First is a slope barrier plan. The underground workshop is arranged in the mountain. The ground workshop is ranged on the platform outside the slope, and the underground workshop and the ground workshop are arranged on the same elevation. The secondary circulation cooling system is adopted, and the cooling tower is designed as a single tower. When multiple units are arranged, each unit shall be arranged as a purple public facility, external traffic, and anti-seepage curtains between units may be shared. The level earth barrier plan is the underground workshop is ranged in the mountain. The ground workshop is ranged on the platform outside the slope, and the underground workshop and the ground workshop are arranged on the same elevation. Discharge reactor building cavity surface above the platform layout construction yard, on top of the reactor building cavity layout, hosting shaft connected to the surface. For the construction within the reactor building containment, structural and related equipment, hoisting, transportation. Formal nuclear power plant operating using concrete backfill closed and in the construction of discharge platform arranged pool, high building fire pump room, and etc. Third is the underground barrier plan. The ground workshop is arranged on the upper terrain or platform of the hillside, while the underground workshop is ranged in the mountain below the terrain at platform on the vertical surface. The ground workshop is located above the underground workshop. The underground workshop and underground workshop are mainly connected by vertical shaft. 3 vertical shafts are arranged at the top of workshop, which are respectively used as main steam pipe, main water supply pipe, and personal channel. A shaft is arranged on the roof of the fuel plant to serve as a fuel transportation channel, and a shaft is arranged in the nuclear oxidation plant to connect with the surface. Last but not least, the fuel barrier plant. All buildings of the underground nuclear plants are arranged in the mountain body. The nuclear island plant is arranged on the inside. The conventional island and afflicted plant are arranged on the outside side. Nuclear plant part and the scheme of slope-type flat barrier layout is the same. Other factors, including electric and diesel generator factor, run the service workshop. Air compressor, fire pump, turbine factor, and so on. The consolidation arrangement is 2 sides large hole indoor. The turbine and operation service factor indoor place themselves in a hole. The inside on the mountain, the size is about 137 meter, multiple 33 meter, multiple 58 meter, and the connection factor Kelvin span is 70 meter. Electric gas, diesel generator factor running in a hole in the indoor service building layout, and the turbine factor Kelviner barrier arrangement. The size is 77 meter, multiple 30 meters, multiple 52 meters, and the spacing between the 2 cavities is 50 meter. The design of seepage prevention and drainage of underground cavern. Underground cavern parallel arrangement. The size is 77 meter, multiple 30 meters, multiple 52 meter, and the spacing between the 2 cavities is about 50 meter. The design of seepage pavement and the draining of underground cavern group. External crossing and pipeline is the same as the basic plan of slop barrier. Due to the huge structure size of the cooling tower in the secondary cooling mod, it is not suitable to the arrange in the mountain. The primordial cool mods should be adopted to divert water from nearby water sources for cooling. And from this report, I learned the dispensable of human society on the nuclear energy in the future. Nuclear energy has been development for the past 5 to 6 decades, and people are relying more and more on the nuclear energy. The advanced reactor technology faces many challenges, and the first one is the technology perspective, and to solve the safety perspective, we proposed to build the nuclear power plant underground, and that's a new solution for that. And this is my presentation. Thank you.